Hello, and welcome back to another episode of the Curiosity Monkey podcast. Now, apologies, it's been a while since we've done another episode because, we've all been quite busy with different things, but now we should be back and we should expect a few more episodes upcoming over the next couple of weeks. In this episode, we're going to be covering quite a cool topic, in my opinion, and I'd say this topic isn't particularly necessarily well known by general people. So this topic is related to climate, and it's on aerosols and clouds and how they interact with the climate. Now, clouds are pretty cool, in my opinion. There are a large variety of different clouds, and they often look kind of pretty. They can look kind of dark and grey and angry on stormy days, or they can look very nice, light and fluffy. They can be light and thin, high up in the atmosphere. They can be low down, thick clouds that cause thunderstorms, heavy rain, for example. And clouds are important for many reasons, and we'll cover this in the episode. But you'll probably know they provide water through precipitation, which is important for life. But they are more than just important for life and for providing water through rain. They're also very important for influencing the global climate as a whole. And to understand why clouds are so important, we need to understand how they are formed. So part one of this episode is looking at aerosols and cloud formation. So to begin with, aerosols are small particles of liquid or solid suspended in a gas, such as in the atmosphere. So aerosols are always about in the atmosphere, but they vary drastically by number. So the number in a given amount of air, the size of these aerosol particles, and also the composition. So what is it made of? What's its chemistry? And the reason we're talking about aerosols in regards to cloud formation is because aerosols are very important, as they are things that water vapor condenses upon to form clouds. So maybe you weren't so aware that aerosols are around us in our air right now. So if you breathe in, if you're wherever you are, even in polluted environments and natural environments where there's very little pollution, there are still loads of aerosols around you. But they do vary depending on where you are. So polluted regions tend to have a lot more aerosols of anthropogenic origin, meaning man-made origin. And natural environments can be very clean in terms of aerosols, meaning they might not have loads of aerosols in the air, but other natural environments also emit very large amounts of aerosols. For example, forests, during summertime, they can emit large amounts of these volatile organic compounds into the atmosphere, which can be converted into aerosol compounds. And these can be dominant over these regions. And also, when I talk about aerosol, people who don't know necessarily much about aerosol can often think that all aerosols are bad, when really it's just a small subset of these that can cause human health problems. So what are some sources of aerosols? So I mentioned that aerosols are emitted from many different sources, both natural sources and anthropogenic sources, man-made sources. So a couple of natural sources include sea spray. For example, if you have wind blowing through waves, that can release loads of spray particles, small, fine particles of salt and water. And this sea salt aerosol is generally a coarse, so relatively larger size than other aerosols. And you can also have slightly smaller sea salt aerosols through bubble bursting, where you have, again, air is forced into water, and then the bubbles of air in the water burst, and they kind of release small droplets, tiny droplets, into the atmosphere of sea salt. Another big one is dust. So think, say, deserts or just dry areas in general. Wind can transport small particles across the surface, and this can really hook and waft small particles of dust up into the atmosphere, and then these can get carried actually thousands of miles away in wind currents even to other countries. So in UK, for instance, we get a few days a year we'll have days where Saharan dust has blown all the way across the ocean and gets deposited in the UK. There's also dust from the Sahara being blown all across to South America, where it's thought that mineral dust has helped fertilize the Amazon rainforest. And then again, earlier I said the biological aerosols. So you've got pollens, you've got aerosols emitted by trees, you've got aerosols emitted by planktons in the ocean, and then natural somewhat. I'm kind of putting this natural / anthropogenic. It's also wildfire smog. So wildfires release carbon particulate particles and sulfate particles, and this is natural because wildfires do occur naturally, but also anthropogenic activity can increase risk of wildfire. Say just the warming from climate change, and most wildfires are started accidentally by men or humans. Another natural one is volcanic ash and volcanic sulfate. So that's emitted up high into the atmosphere. It can interact with solar radiation. After some big volcanic eruptions, you'll notice that leads to a period of cooling afterwards due to the way the aerosols interact with the incoming solar radiation. And anthropogenic, there's many sources, but a couple, again, dust, but from, say, roads or dust from industry. And a big one is sulfate from the burning of fossil fuels. So these aerosols exist in the atmosphere in varying concentrations, depending on location. And the size range is from just a couple of nanometers, quite small, to the whole micron scale, or micrometers. So how do aerosols relate to clouds and their formation? Well, clouds form when the air becomes supersaturated with water vapor, leading to the condensation of water onto atmospheric aerosols. So supersaturation is when the relative humidity in the atmosphere is greater than 100%. And the relative humidity is just saying that when the partial pressure of water vapor in the atmosphere is greater than the partial pressure of water vapor at equilibrium in the atmosphere. So essentially, another term for this is when the air has reached its dew point. So how is supersaturation generated? So most of the supersaturation is generated when the air rises. So if you imagine a parcel of air particles with imaginary boundaries at sea level. Now updrafts drive the ascent of this air parcel. Atmospheric pressure decreases with height, so a parcel of air presses on these imaginary boundaries due to the pressure differences, causing an expansion of the parcel. Expansion is caused by a force that moves the boundaries. Thus work is done and internal energy of the parcel decreases. So the internal energy is a function of temperature, and the temperature decreases because of this. And the ability for air to hold water is an exponential relationship with temperature. So higher temperatures can hold much more water than lower temperatures, and it goes in an exponential fashion. So a reduction in temperature will cause a reduction in the capacity of the air to hold water. So the air becomes supersaturated with water vapor. Basically, it can hold more water. It's holding more water than it would want to at equilibrium. And water preferentially condenses out onto aerosols rather onto itself in homogeneous nucleation, because aerosols provide a surface that facilitates the condensation process. Homogeneous nucleation occurs when the water molecules in the gas phase collide to form a nucleus of liquid or water or solid water ice. Now the size of this nucleus is limited by the frequency of collisions in the atmosphere, which tends to be quite low in a typical air parcel. So the size of the nucleus, because it's limited by the number of collisions, tends to be quite small. It's very uncommon for many collisions of water molecules simultaneously in the atmosphere to form a large nucleus. This only happens when the atmosphere is holding very large concentrations of water vapor, such at very high supersaturations. And these levels of supersaturations are not usually found in most places in the atmosphere. So as I say, it limits the size of the water nucleus to be quite small. And small droplets have a greater curvature. So the surface tension is lower on this droplet, which means the work required to overcome the surface tension is less. So this means you need higher vapor pressures are required to keep the droplet in equilibrium with the atmosphere. So these small droplets tend to just evaporate away, as this supersaturation does not exist in the atmosphere. So homogeneous nucleation is relatively uncommon. So aerosols offer a surface for water vapor to condense upon without immediately evaporating due to their already larger size. Additionally, If the aerosol is water soluble, then this further reduces the supersaturation required for condensation. This is because solute molecules block some of the surface, preventing evaporation. So say for our sea salt aerosols earlier, there'll be some salt particles blocking the path of water molecules trying to evaporate. This means that you have a lower rate of evaporation, so lower vapor pressures are required to keep it in equilibrium. So water vapors will continue to condense onto these aerosols as long as there's sufficient water vapor in the atmosphere. Now these droplets will continue to grow in the atmosphere as long as there's enough water vapor. So essentially aerosols allowed cloud droplet formation at much lower relative humidities than without it. When the drop becomes large, growth by condensation, so condensation onto aerosol particles, becomes inefficient due to its large size. So further growth then has to occur through other processes, such as collision coalescence, where droplets collide and merge to form larger particles. And when droplets become large enough, they begin to fall out the atmosphere as raindrops. However, many clouds do not lose their mass through rain. Many just evaporate away back into the atmosphere. Additionally, while we're talking about aerosols, we can talk about their effects on the climate. So some aerosols directly interact with sunlight, causing scattering of solar radiation back out to space, which can lead to a cooling effect, because you're reducing the amount of energy that the Earth receives. Some aerosols can cause a warming effect by absorbing solar radiation. Additionally, because aerosols can seed the clouds in the atmosphere, these clouds then interact with both shortwave and longwave radiation. That can lead to either a cooling or warming effect, and we can talk about this in a second. But there is evidence to suggest that anthropogenic aerosol emissions actually have offset the effects of greenhouse gases in some areas. And this is why the northern hemisphere shows slower surface warming than the southern hemispheres, because the southern hemisphere is less polluted with anthropogenic aerosols, which means there's reduction in this cooling effect. And there's some concern because reduction in air pollution, especially over areas of Europe and North America, has caused a reduction in the aerosol emission. And this has kind of started to unmask some of the effects of the carbon dioxide-induced warming. So how do clouds influence the climate? So, as I say, clouds are not just important for the water cycle, but also very important for influencing the global climate. The energy released by condensing vapors drives global circulation in conjunction with the Earth's rotation. And as said before, clouds also interact with radiation, both from the sun and from the Earth. Now, dense, thick clouds are excellent reflectors of visible light from the sun, and sunlight does not penetrate far into the cloud before reflection, and hence why you see clouds, say if you're in an aeroplane, bright cloud tops, and if you're underneath a big thick cloud, it tends to be darker, greyer cloud bottoms. Now, higher and thinner clouds tend to reflect less, as they have lower droplet concentrations and a smaller path for light to penetrate through. Thick white clouds promote cooling due to reflectance of solar radiation back into space, and this decreases the total energy absorbed by the Earth, as most of the solar radiation from the sun, if it does reach Earth's surface, is absorbed. So having this reflective layer can reflect a significant proportion of energy back out to space, which can cool the planet. And all bodies emit radiation at a wavelength corresponding to its temperature. The Earth emits in the infrared range of the spectrum. Clouds absorb this long-wave radiation well, leading to a warming effect, especially in the thicker low clouds. The water in the clouds then radiates this radiation at its temperature, so in the infrared spectrum, in all directions. So that means both upwards and downwards. So some of this radiation is lost back out to space, and some of this comes back to Earth. So this effectively is what the greenhouse effect is, but on clouds, by clouds, as you're directing more energy back towards the surface of the Earth. So it kind of warms the surface, acts as a blanket. So it seems that the cooling effect of reflecting solar radiation back up to space outweighs the warming in the daytime in the low, thick clouds. But at night, you'll notice that clouded nights are much milder than clear nights at a given time period, because the energy is lost to space quite quickly when it's a clear night. But with the clouds, it acts as a thick insulating layer. It keeps the planet warm. The high clouds are thinner, thus reflect less solar radiation, but they still absorb a fair amount of infrared from the Earth and irradiate this some of this downwards and some upwards, like the low clouds. And it seems like these clouds, due to them reflecting less radiation back into space, contribute to more of a net warming effect. So it's clear that different clouds respond very differently to radiation, and this can net warm the Earth or net cool the Earth. However, it's even more challenging to predict how cloud properties and coverage will change as we move to a warmer climate. Cloud formation and corresponding cloud properties depend on so many interacting factors, meaning there's so much uncertainty over how clouds will change in the future as we continue to emit carbon dioxide. Carbon dioxide induced warming can affect aerosol emission and supersaturation generation. For example, warmer climates will cause more water vapor to be emitted into the atmosphere because of the higher temperature. Also, the temperature of the Earth can affect general meteorology, such as the wind fields that can affect aerosol emission, such as the emission of sea salt aerosol, the emission of dust aerosol. It can also cause the differences in productivity of plants. So photosynthesis and the metabolisms of plants tend to be higher when it's warmer. So this could cause more production of aerosols. And these aerosols could lead to higher cloud production and higher cloud coverage, and also maybe higher albedo of the clouds, so brighter clouds. And this could lead to a cooling effect. You could also get changes to the lifetime of clouds, as more aerosols emitted, both naturally or unnaturally, could lead to higher droplet numbers, but also smaller particles, and the smaller particles tend to remain longer in the atmosphere at a given supersaturation level. As the small droplets will survive longer. Clouds existing for longer could reflect more light, leading to a cooling. So this is a negative feedback example, where the increase in temperature due to carbon dioxide causes change that brings back down the temperature. Negative feedback. However, it's also possible that you get positive feedback effects, where the higher temperatures cause evaporation of clouds, which leads to less reflectance and then more warming. So this is where an increase in temperature will lead to a further increase in temperature. So as I say, there's much uncertainty over how clouds will respond to a warming climate, and whether they could lead to a negative or positive feedback effect. But that's about everything for this episode of the Curiosity Monkey podcast. Now, I think clouds are quite cool. I also think people do know quite a lot about global warming now, because it's very well talked about, as it should be. But there are a lot of other factors that can influence the climate, and these are very important to consider. And I think clouds, they're also very cool anyway, but they have such a big impact on our climate that I think it was a good episode to talk about. Now, I thought I would end on a quick, fun and exciting cloud quiz. It's just 3 questions that you can have a go at answering. I'll say the answers. Now, question 1. How much does a typical cumulus cloud weigh, assuming its volume is 1 kilometer cubed? Now, the answer to this may or may not surprise you, but if you take like half a gram per meter cubed liquid water content, then we find that the mass of the cloud is approximately 600 million kilograms. Now, the second question is, how high are the highest clouds that we find in the atmosphere? Now, these clouds are called noctilucent clouds, and they can be around 60,000 meters up in the atmosphere. Now, this is pretty high considering the cumulus cloud we were talking about earlier was around 1 to 2 kilometers high in the atmosphere. Question 3. What is the percentage of the Earth's surface covered by a cloud? Now, one study estimated that 67% of the Earth's surface is covered by cloud, which is quite a lot, actually. So, I hope you enjoyed that episode and the little quiz at the end. But that's everything for this episode of the Curiosity Monkey podcast. I hope you enjoyed learning something about clouds and how they interact with the climate. Now, the Curiosity Monkey should be back with a few more episodes coming up. So stay tuned for that. If you wish to give us some episode suggestions, then you can email at thecuriositymonkey1@gmail.com, or you can follow us on Instagram at thecuriositymonkey. And please don't forget to give us a rating on Spotify or whatever platform you're using, because this helps promote it. So yeah, thank you for listening, and see you in the next episode.